Okay, so it's my pleasure to introduce Onur Mutlu. Mutlu is really an inappropriate name. It should be Onur Yoğun. And if you don't understand Turkish, you'll have to ask some Turk, you know, what that means. Onur got his undergraduate degree in Michigan. And he did not get A+ in every course he took at Michigan, only the ones that were important. If they weren't important, he just got A. And then he went on to Texas, got his PhD at Texas, where he was awarded the Distinguished Excellence in Research at his graduation. His dissertation was submitted to ACM as for the top dissertation award. Then he spent a couple of years at Microsoft, where he hired summer interns. And these interns from the various universities, if you look at their list of papers published, you will see that they were at these universities and they got papers published in random bullshit conference number 1, 2, 3, 4, and then one in ISCA, or Micro, co-authored with their mentor, Onur Mutlu. Then he went to Carnegie Mellon, where he's been since, and he now holds the William D. and Nancy Strecker mid-career endowed professorship, which means they had to lengthen his business card to include all that on his business. He is burning up the field. He's the most productive researcher in computer architecture in the community. I don't think anybody would disagree with that. And we're lucky to have him here today. He's going to speak on rethinking memory system design for data-intensive computing. And probably for other things also. Onur.
Okay, thank you, Yale. Appreciate the introduction. It's a great pleasure to be here. I've never been to Greece before, even though I've been very close to Greece. And this time I made the jump. Although this is not the closest island to Turkey. There's one more island which I'm sure Yale knows about. That's okay, we can ask later. I'll talk about rethinking memory system design, and I should really remove that for data-intensive computing because it's really redundant. Everything interesting is data-intensive today. And since Yale tells me that I should really be speaking at half the speed I should be speaking at, I really appreciate the extra 30 minutes that we were just given by Carlo. Okay, so if I think we have enough time. This is a really long talk. Feel free to ask questions in the middle. We don't need to cover everything over here. And I think we have around an hour and 20 minutes, right, Carlo? Plus the 30 minutes.
No, 1 hour and 20 minutes in total.
Okay, so let's get started. We'll talk about main memory, which sits in between processing units, computation units, and storage. It's a critical component of all computing systems that we have today, whether you're designing server, mobile, embedded, desktop, or sensor systems. You need to have some working storage, which is really the main memory. And this memory system must scale in many, many dimensions: size, technology, efficiency, cost, and the algorithms we use to manage it, in order to maintain the performance growth and the technology scaling benefits that we've been used to for a long time. This is another view of the memory system. I'll make just 2 points here. It's a very cartoonish picture. If you look at it, these are the computation units, the red parts. Everything else is really dedicated to data storage and movement. It's the interconnects, shared caches, other shared memory controllers, other buses, shared memory. It's all data storage and movement. And it's most of the system that we design today. If you look at the bigger system, it's all also like this. And the second is it's a big shared resource. And even if you look at these red parts of computation units, there's memory in it, the register file, L1 caches, and the interconnect. So most of the resources that we have today, we're really dedicating to memory. So let me tell you a little bit about the state of the main memory system as I see it today. There are some recent technology, architecture, and application trends that lead to some new requirements from this system and that exacerbate some old requirements. And we've always demanded a lot from this system. I'll posit that DRAM and memory controllers, as we know them and as we design them today, are unlikely to satisfy all of these requirements. And there are some emerging memory technologies that happen to be non-volatile that enable some new opportunities, like this merging of memory and storage, which we will hopefully get to. So given these trends, we need to rethink the entire main memory system to fix the issues that we're having with DRAM and hopefully enable at least one of these emerging technologies while satisfying all of the requirements. This is an outline of what I have in mind. I'll talk about some of the major trends affecting main memory today. I'll pose everything as a memory scaling problem and talk about two major solution directions. And circle back a little bit and talk about, derive some principles hopefully, and talk about how we can scale forward. These are the three major trends, as I see them, as affecting main memory. First of all, we're demanding more memory capacity, bandwidth, and quality of service. And this is really driven by three major trends. We're putting increasingly more agents on the chip, multi-core or heterogeneous multi-core. Applications are becoming increasingly data intensive. There's increasing demand and hunger for data. I recently attended the International Symposium on Molecular Biology, and it's amazing how much data, genomic data, that we can generate. We can actually generate much more than we can efficiently process today. Consolidation is another trend. Cloud computing, GPUs, mobile and heterogeneous systems, we're consolidating more and more applications on the same chip for efficiency reasons. Building efficiency, area efficiency, energy efficiency. So all of these require more capacity, bandwidth, and quality of service from the memory system. And this is one example showing the memory capacity gap. This is actually from a paper that was written by University of Michigan and HP Labs in ISCA 2009. Basically, they've shown that core count is doubling approximately every 2 years, and the DRAM DIMM capacity is doubling approximately every 3 years. And if we continue this trend, memory capacity per core is expected to drop by 30% every 2 years. Now, if you want more features out of the software, and if you want programmers to stay sane, this is probably not a good thing to expose to them because they're getting less memory for the threads that they're writing. And if you actually do the calculation for memory bandwidth per core, the trend is much worse. The exponentials are different because memory bandwidth is increasing by approximately 10% per year. So the second major trend, not necessarily new, memory, energy, and power is a key system design concern today, and it's been so for a while. There's this nice paper by Charles Lafergie et al. That was published in IEEE Computer by IBM Research that showed that about 40 to 50% of the entire system energy of the big iron servers that IBM actually manufactures is spent on the off-chip memory hierarchy, including the off-chip interconnect, off-chip caches, DRAM, and the storage. And one issue we have with DRAM working memory is it consumes power even when it's not used. So we can design terabytes and petabytes of memories, but we need to refresh them every 64 milliseconds. And this is a scaling issue, which we will get to, hopefully. So on top of this, DRAM technology scaling is actually ending. And if you don't like the word ending, you can say getting extremely difficult. And I will actually give you some evidence from the field showing this. ITRS, International Technology Roadmap of Semiconductors, has been projecting for a while that DRAM will not easily scale below X nanometers. And I like putting X over here because I don't need to change the slide when X changes. And ITRS comes up with their new roadmap. But basically, reducing the size of the DRAM circuit to a smaller node has provided many benefits. We got higher capacity, we got lower cost, and we got reasonable energy scaling. And if this doesn't continue, then it's going to be very difficult to actually provide both of these over here. So these are all really interrelated with each other. Okay, let me actually pose everything as a memory or DRAM scaling problem, and let's look into some solution directions in a little bit. But I'll motivate the problem a little bit longer, because I'd like to show some evidence from the field that this is actually a real problem that we're facing today, and you may be facing in the systems that you're running today. So, if you look at DRAM, you actually need only the capacitor, right? That's where the charge storage resides. It's charged or discharged. But in order to be able to determine whether it's charged or discharged, you need an access transistor, and you need to sense the charge using charge sharing, using a sense amplifier over here. Now, for this to work, this capacitor must be large enough for reliable sensing, and this access transistor should be large enough for low leakage through this RC path and high retention time. And as you reduce the size of the circuit, the feature size, both of these properties become very difficult to maintain. And DRAM manufacturers have jumped through a lot of hoops to actually make this work for a long time. And this was actually the value that was assigned to X by ITRS in 2009. They said reducing the feature size of this below 35 nanometers is challenging. And if you're following the DRAM industry, we're actually at the 20 nanometer node today, maybe actually high teens. So we actually gone beyond 35 nanometer. It has actually come at a cost. It has become certainly very difficult. And I'll give you one example my students have characterized heavily. Yoongu Kim actually did this work. Basically, if you take a DRAM chip that's off the field today, you can induce errors in that chip using the following mechanism. you have a bank of DRAM, and when you access a bank, you need to actually access a row. So you need to activate that row with high voltage. And then if you actually deactivate that row by what's called a pre-charge, and if you keep doing this, activate pre-charge, activate pre-charge, activate pre-charge, over and over, enough times within a refresh interval before the row is refreshed, you actually start getting errors in adjacent physical rows that have nothing to do with this row. And this happens because of electrical disturbance. The cells are too close to each other. As you apply a high voltage and low voltage, what you're doing is you're exciting the charge leakage in the cells around this cell. And this is actually very fundamental to memory. This is really nothing new if you think about memory. Flash memory has this kind of mechanism. It's called read disturb. Hard disk, even hard disks have this kind of mechanism. It's called adjacent track interference mechanism. It's not exactly the same, but the high level problem is the same. It's really disturbance. So we call this a hammered row, and these are the victim rows. And we've actually shown that you can do this attack, if you will, in most DRAM chips today. My students tested chips, many chips from multiple different companies, major manufacturers of DRAM, and more than 80% of the chips that they've tested actually exhibit these errors. And once you have this error mechanism, you can actually easily write a user level program, which consists of these following 7 lines, that can actually do this attack while you're, of course, by carefully constructing it. Basically what this program does is it ping pongs between 2 rows over here in a bank and cause errors in memory. And you can actually do this on a real system. There's nothing fancy about Intel and AMD. If you take an Oracle chip and put the right DIMM over there, you can actually do that as well. Basically the errors, the number of errors you get is proportional to the number of accesses you can actually make to memory, sustain to memory. Because what we're doing is we're causing the errors before the cell is refreshed. If you can do many, many accesses before the cell is refreshed, you can actually cause accelerated charge leakage to flip the bits. So this is a real reliability and security issue, and in a more controlled environment you can actually induce many errors. But why is this a scaling problem? It's a scaling problem because it didn't used to happen before. So disturbance is actually very old. It happens in all the chips, and DRAM manufacturers were able to prevent it. And they were actually successfully preventing it until 2010, and the chips we tested before 2010 actually didn't have these errors. The first appearance actually happened in 2010. And all of the chips that we have tested between 2012 and 2013 actually had this error mode. It didn't matter which manufacturer it was from. So it was very fundamental in my opinion. Basically, they ran into this issue and they weren't able to test for it. And testing for it actually may be very difficult. So we've actually designed infrastructure to do a lot of these studies on DRAM. We've characterized the error. I'm going to skip over a lot of these. I'd be happy to talk about the infrastructure as well. And you can read the paper on our characterization. And we've actually covered the solution space as well. The solution actually, so one solution you can imagine is you can refresh DRAM much more frequently. Right? Back in the paper we've shown that you need to refresh DRAM 7 times more often than today, what you're doing today, to actually get rid of all of these errors. So it comes at a cost. And you have to talk about some of the other solutions. It's pretty interesting. So if you buy a DRAM chip in 2015, I do not believe you're going to see this kind of error mechanisms, but you may see it in some other technologies. But there may be other error mechanisms that are coming going forward. And why is this scary in terms of the system level? I think there are interesting security implications because when Jung wrote this paper, what we had written was memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And I still believe that, otherwise how can you build a reliable system on top of this kind of hardware? Basically, Google actually took this and they've actually designed an attack. I really recommend looking at this website. This is their security team. They actually took our paper and the code, and they've actually designed an attack. What they did was, they were able to induce errors into the chip reliably, such that you could flip bits in your page table as a user level process, and you would flip the right bits in your page table such that you can get write access to your own page table. And once you get write access to your own page table, you can actually get write access to your entire memory. As a result, you can take over the system as a user. And this is pretty cool. You can download their code. They don't have this code, of course, to attack, but they have the code to actually do the hammering much more efficiently. And this was called the row hammer vulnerability afterwards, and people actually came up with things like this, thinking memory is dead or something like that. I do not believe memory is dead. This talk is all about memory is actually important to look into, but this is to motivate. So let me recap the DRAM scaling problem. So we have evidence from the field that this is becoming difficult, and there's no reason to believe that this is going to become easier on the manufacturer's part. Because if the charge-based storage, as you reduce the storage of the size of the charge storage unit, it becomes, all of the two properties, reliability and retention time, become very, very difficult to maintain. And actually, Samsung and Intel wrote a paper related to this, which I would definitely recommend, which was published in the Memory Forum 2014. This is Samsung DRAM design team and Intel's memory controller team. And they've actually identified three major process scaling challenges at the low level with DRAM. They said refresh is a big challenge. They said VRT, variable retention time, is a big challenge. These are actually related. As you reduce the size of the storage unit, you need to refresh it more frequently. And it becomes difficult to figure out how often you need to refresh it. VRT refers to that problem. There's a random process, a physical process, like quantum-like process in a sense. Basically, a cell retains time for a short time, for a long time, for days and days, if you will. It can retain, actually a lot of the cells in DRAM are very strong. They can retain charge for seconds and seconds, hundreds of seconds. But then there's a point at which charge gets trapped in the cell, and this happens to be a random process. At that point, the retention time drops down to 8 milliseconds or so, or 64 milliseconds or so. So it becomes very difficult to test these cells to figure out what's the minimum retention time of a cell. As a result, you don't know how often to refresh it. And this is difficult for the manufacturer. And what makes it worse, the problem worse is, the manufacturer may not be able to determine this, because once you actually take the DRAM chip and solder it on a board, you're actually exposing it to very high temperatures, and that high temperature changes the profile of the retention time of the cells. So maybe someone else needs to do it. Anyway, I would definitely recommend this 4-page paper. So how do we solve the problem? Given that we definitely have a scaling issue, I think there are three major solutions, and there may be more. We'll have to talk about it on the boat tour or something. First of all, we may want to fix it. And fixing it is probably not going to happen at the device or circuit level. So we may want to make the DRAM and the controllers more intelligent. Just like the approach that has been taken in very unreliable memories like flash memory or hard disks. We may want to have new interfaces to DRAM, new functions in DRAM, and new architectures. I call this the system DRAM co-design. It's actually similar to what these two teams came up with, co-architecting controllers and DRAM. The second solution direction is maybe we want to eliminate or minimize it if it's possible. If you can find a technology that can replace or more likely augment DRAM that doesn't have this kind of scaling issues, we can enable that technology, and maybe this can enable a system-wide rethinking of memory and storage. So I'll talk about this in a little bit. And the third solution direction, which is also interesting in my opinion, is to embrace it. Maybe we say some memory is unreliable and we can manufacture it at very low cost, and we can tolerate it in some way. But then some memory is reliable, and we can partition our data intelligently across these different types of memories and still get good scaling in terms of memory in the system. This may lead to new models for data management and maybe usage as well. And there may be other solution directions. But regardless of which solution direction you take, in my opinion, the solutions to memory scaling will require software, hardware, and device cooperation, and increasingly so. It's going to be very difficult to fix the problem at one level. We may be able to fix it at specialized domains, and this is something that I stole from Yale's lectures. And although I included the user over here too, because I think it's an important component of the system. Okay, so let's take a look at some solution directions. I'll talk about three solution directions and then diverge a little bit to talk about a really important problem which I will not go into detail about, and then we'll go into details in each of the solution directions. So the first solution direction is fixing DRAM. We'd like to overcome DRAM shortcomings by designing the system and the DRAM together. In a sense, this is like I think of it as punting the DRAM's problems to the other parts of the system. But this has been done really successfully in flash memory, for example, and the hard disk as well. So this will lead to new DRAM architectures, interfaces, and functions, and we probably should be doing better waste management because we're really wasting a lot of memory today. There are several key issues to tackle. In my view, we need to enable reliability at low cost, reduce energy, and these are actually two sides of the same coin in a sense. You can always increase your reliability by expending a lot more energy, refreshing more, adding more ECC. If we need to improve latency and bandwidth, we need to reduce waste, and there's a lot of waste in capacity, bandwidth, as well as latency, and I'll show you some examples of this. And I think there's a really important issue, if you will, that can fix a lot of these issues, and that's enabling computation close to data. If you actually do computation where it makes sense, instead of where we do it today, then we can actually get rid of a lot of these scaling issues. And these are some of the works that my students have been doing in the area. I'll pick and choose from some of these. The second solution direction, which is equally interesting, is enabling emerging technologies. There are some emerging resistive memory technologies that seem to be more scalable than DRAM, and they're also non-volatile on top of this. One example is phase change memory. At the same time, ITRS said DRAM will not easily scale below 35 nanometers. They assigned a value of 9 nanometers to phase change memory, and it seems to be lower than that actually at this point. And it's expected to be denser than DRAM because you can chop up the resistance range into multiple bits per cell. The problem is these emerging technologies, of which phase change memory is an example, there are other examples, STT-MRAM, or memristors, if you will. The key question we're asking is, they all have some issues. The key question we're asking is, can they be enabled to augment, replace, or surpass DRAM? So I'll talk about a little bit of that toward the end. I think a more viable solution direction going forward is the third direction, which is designing hybrid memory system. And people have searched for a memory that's good at everything, every parameter, basically green at every dimension you can imagine, every metric you can imagine. I think that's going to be very difficult to achieve. So why don't we actually say there are some memories that are good at some things, bad at some other things. There are some other memories that are good at some things, bad at some other things. Put them together intelligently and design the hardware and the software to manage data allocation and movement to achieve the greens as much as possible without exposing the reds, while exposing the reds as little as possible. And I'll talk about this a little bit too. So before, I'll give you one example of this in terms of reliability. So if you know your application well, or if you can somehow figure out the memory error vulnerability of different data in your application, perhaps you can characterize it. And you can say there's some parts, some data in my application that, if there are errors, if there's some amount of error, I can tolerate it. Video, images, for example. And there are other parts of my application, maybe the index to a database, where I cannot tolerate the errors as much. So if we can characterize this data somehow as vulnerable and tolerant, we can perhaps map this to reliable and low-cost memories. And we can actually achieve significant savings. Perhaps this low-cost memory can be even lower cost than what we have today. The DRAM manufacturer may not test it as much. And we've actually done this study on Microsoft, together with Microsoft. My student Yishin Guo actually did this study. And they've shown that on Microsoft Web Search workload, you can reduce server hardware cost by around 4% or so, while achieving still good availability targets. And this is single server availability. You can actually, with the distributed system, you can have much better availability with this kind of system. So I think this is a really interesting solution direction as well. Let me tell you about one more problem, and I will go into more detail in some solution direction. And this is the problem of memory interference. I think this is orthogonal to everything we've talked about so far. Regardless of what you design memory with, as long as it's a shared medium across different agents over here, you'll have the problem of interference between those agents when they're accessing the shared main memory. And the problem is today, most of that memory interference is uncontrolled. You can have a memory controller that's unfair over here, that prioritizes one core over the other. As a result, you may be actually running 1,000 different applications, but you may be getting very little performance across all of them. Because memory interference is uncontrolled, you get unfairness, starvation, and low performance. And as a result, we have an uncontrollable, unpredictable, and vulnerable system. So the solution that we're following, which is kind of obvious actually, is quality of service over memory systems. And this is also hardware-software cooperative. Basically, we would like to design the hardware to provide a substrate that the software can configure, but the hardware can be fair. So we've been looking at application over memory scheduling, memory partitioning, and core throttling mechanisms. And the software can design and configure these resources to satisfy different quality of service goals. When you actually want to provide performance for an application, you can actually adjust these knobs. And this problem actually is going to, I'm not going to talk about the solutions, I'll talk about one solution direction. This problem is going to become much more difficult going into the future because the systems are getting more complex. We have these heterogeneous agents, they're increasingly heterogeneous, and we have this heterogeneous memory that's also increasingly heterogeneous. And the key question is how do we allocate the resources to these heterogeneous agents to mitigate the interference and provide predictable performance. For example, the GPU may need predictable performance at times, at other times it may not need that predictable performance. So one solution direction that we're following to provide strong memory service guarantees, this is the work of my student who graduated, Lawan Subramanian, basically is to develop techniques or models that can accurately estimate the performance loss of an application when sharing resources with another application. If you can actually get good estimates for that, now you can actually prioritize the applications and do the resource partitioning well to achieve the performance required for all applications. I'm not going to talk about this direction. You can actually take a look at this paper over here. But the key is doing this all the while providing high system performance, because predictable performance is not a problem if high system performance is not a concern. You can always say, I'll design a 1,000 core system and I'm going to run one application in one core and nothing else. Okay. Any questions so far? Am I going too fast? Did I dial it down to 1/4 of the speed? No?
I think you're fine.
Okay. Yes, there's one at the end.
Yeah, just an overview kind of thing. Existing techniques like chip build and so on, how do you think they perform in terms of the reliability issues you raised just now? Are they sufficient? I guess they increase power, they might increase the cost and so on, but are they sufficient? Do we need to do more better, actually coding and so on?
Yeah, that's a great question actually. I think we need to do more. And we may actually need more reliability in DRAM. More error correction methods. In fact, the paper that I mentioned to you, the 4-page Samsung and Intel paper, one of the solutions they said to the VRT problem, variable retention time problem, is in DRAM ECC. This was a huge no-no for DRAM designers for decades, because they optimized for cost per bit. And using some of the rows for error correction internally in the DRAM chip, that was religiously bad. But now they're actually proposing that as a solution, because they're actually seeing the scaling issues. So I think we need to do more. So in the paper where we characterized the row hammer, we showed that existing ECC techniques are not actually enough. You need double error correction to actually fix all the errors. But I think there's always an issue with ECC, right? You always trade off energy and power and some latency as well. So coming up with intelligent error correction methods for DRAM is definitely a good direction.
So that also should be enough. Actually, I do have a very big question, but I was thinking of waiting until the end.
We can wait till the end.
Because I don't want to derail it.
Okay, sure. One more from Trevor then.
Do you see a future for DRAM?
Let's talk about that when we get to the non-volatile part, or maybe after. Okay. I think there's a future for non-volatile technology in general, maybe not necessarily just for DRAM. Very quickly. Okay, so let me talk a little bit more, in a little bit more detail about some promising directions. So I'll talk a little bit about new memory architectures. I think we need to rethink DRAM and also flash memory, and I don't have time to talk about that. But flash memory is definitely a very good technology for a non-volatile memory, and perhaps an extension of the main memory as well. The second is enabling emerging non-volatile memory technology. I'll talk a little bit about that and hybrid memory systems, and I'll talk a little bit about what we're doing on single-level memory and storage. And this is something I will not talk about, system-level memory storage and quality of service, but I think that's really important. But hopefully I'll convey a lot of hope that we can fix DRAM going into the future with architectural and system-level techniques, and we can enable hybrid memory systems and perhaps single-level stores where we can access data, all of the data, maybe in the world with a single interface. And hopefully we can design predictable systems. Let me jump into the first solution direction, rethinking DRAM. I think we need to do a lot in rethinking DRAM, so I'll pick and choose from some of these. I'll talk first about in-memory computation, because I think it's an idea that's been relatively old, but its time may have come, and it's time to actually re-examine it, make it work. But not make it work in the way it was proposed maybe 30 years ago. Actually, one of the earliest papers on this was from Harold Stone in Logic and Memory in 1970. From IBM. That's actually the earliest that I found. Later, David Elliott Shaw had a paper on the non-mon database machine, which actually proposed the same idea. But I think when things were proposed, putting an entire processor on the DRAM technology is not going to work. So we need to look at it in a different way at this point. There are some technology like 3D stacking where you can put the controller stacked on top of the DRAM die is very promising. And that's where this can actually make it work. I'll talk about a separate direction over here. And I'll start with very basic things. So one approach to enabling in-memory computation is, what can we add minimally to DRAM without changing as little as possible to get the maximal benefits? And I'll start with bulk data copy. So if you look at today's memory, if you want to copy one page to another page in memory, we go through a lot of hoops. Basically, we go through the processor, copy the source page byte by byte all the way into the L1 cache, copy the destination byte by byte all the way into the L1 cache, do the copy, and then write back the destination all the way back to memory. If you're, this causes high latency, because you need to do all that round trip. This causes high bandwidth utilization, perhaps on the most important system resource that we have over here. This causes cache pollution, but this can actually be eliminated by doing this through the DMA, Direct Memory Access Engine today. This causes unwanted data movement, so wastes a lot of energy. So for a 4 kilobyte page copy via DMA, not even going through the processor today, it takes about 1046 nanoseconds and 3.6 microjoules, depending on your technology assumptions, but with some sort of DDR3. So wouldn't it be nice if we could actually, if the processor could tell the memory controller, please copy this page to the destination page for me, and the memory just did this. If it's appropriate, when it makes sense, of course. Sometimes this doesn't make sense. If you're going to reuse the destination very quickly, then it may not make sense. So this causes low latency, this causes low bandwidth utilization, actually no data bus utilization over here. This causes no data, no cache pollution, but that, you could have eliminated that today. And this leads to no unwanted data movement over here when you do it intelligently. So I'll show you a mechanism that takes us 1046 nanoseconds to 90 nanoseconds with very little change to DRAM, and this 3.6 microjoules to 0.04 microjoules. And it's actually really simple to do it, because if you look at how DRAM operates internally, it operates at the page level, if you will, or at the block level, or the row level. If you want to access this 8 bits over here, you need to activate an entire row, which brings the data into the sense amplifiers, and then you need to issue a read command from the controller, which transfers only those 8 bits. So we're going to take advantage of this row level operation, and we're going to have the ability to clone the rows. And the idea is very simple. That's row clone. This is my student Vivek Seshadri's idea. Basically, if you want to copy one row to another row in DRAM, when the rows share the sense amplifiers, you can activate the source row, which brings the data into the sense amplifiers. And then at this point, instead of reading the data, what you can do is you can deactivate this row and activate a destination row. What happens at this point is the data that's latched in the sense amplifiers, they start driving the bit lines, and the data gets latched into the activated destination row. So by doing 2 consecutive activates, we can actually do the copy at 90 nanoseconds instead of going through the processor. Yes?
Don't you have to write it back to the first line? I mean, you destroyed the content of that.
No, you need to deactivate. So that's something that doesn't exist today. So that's the additional thing that you need to do. So the second activate should actually deactivate the first one. So actually, this is very little area cost. This one's actually much little area cost than the 0.01%, but we want to actually make it more general. So this works really well if the source and destination pages are actually sharing the row buffer or sense amplifiers, which is this case over here. So when you, in a subarray, the rows actually share the sense amplifiers. What if things are in different banks? So you can actually use the internal DRAM data bus to do the copy internally without actually bringing the data into the processor, and that actually is not as fast as this one, but it's still fast because you're not going through the memory bus. And the hardest part is actually doing the copy when the source and destination pages are actually in different subarrays, but in the same bank. Because you have global bit lines that are being shared across the subarray, you need to do something different over here, which I will not go into. But this is where you get the lowest benefit. So the benefits you get actually are dependent on where your data is located. This is all within a chip. If the data is source and destination are within the same subarray, you can do the copy really fast. So what is the benefit of this in terms of latency? If the source and destination are in the same subarray, you get almost 12x reduction in latency and 74x reduction in energy for a 4 kilobyte page copy. And the benefits actually change if the source and destination are in different banks, so you get less benefit, but you still get significant benefit in terms of energy, regardless of where you do it. And this is the effect on application performance. I'm not going to go into this in detail, but on applications where you have significant copies, like system functions, fork for example, you get significant performance improvement and energy reduction. And this is commensurate with the amount of copying and initialization that you do. Actually, this is when we talk with some database companies that do a lot of initialization of their database, this is something that they like because they do a lot of zero initialization. And initialization is really a special case of copy. To initialize something to 0, let's say, or any value, you just write it to one row and you copy that row to other rows. And this actually provides benefits when you're doing multi-core because the copies get out of the way, you don't consume bandwidth, and other cores now can access memory. So what does it take to actually enable this? You really need end-to-end system design, even for something simple like this. And this is true for any kind of in-memory computation, in my opinion. You have this DRAM base that can do copying very efficiently, and you need to actually do something across the stack. First of all, you need to be able to communicate occurrences of this bulk copy and initialization across the layers. Fortunately, some ISAs actually provide that today. Like repeat MOS instruction actually provides that ability to copy in x86. If you want this to be general purpose, you need to somehow provide cache coherence support, because there may be some data over there in the caches that you may need to flush, such that you need to do the copy. But there needs to be some support for this. In specialized cases, you may get rid of this support. How do you maximize the latency and energy savings? Because you have asymmetric savings. I think system software has a lot to play over here. One of the places where you do a lot of copies is copy on write in system software. If the system software is aware of the topology of DRAM, when it's doing copy on write, it can allocate the destination page from the same subarray. But today we do not have those interfaces. System software actually has no visibility into the DRAM. It doesn't know where the banks are, what bits determine the banks, and it certainly doesn't know what the subarrays are. How do you handle data reuse is important. Actually, if you read the paper, if you do row clone for all copies, you lose performance. Because there are some cases after the copy, the processor needs the data. At that point, you don't want to do row clone. You actually want to keep the data in the processor. So this is actually an important issue. How do you actually partition your computation? So where are we actually taking this? Basically, if you look at a system that we designed today, it consists of a lot of accelerators. And we've always been thinking of accelerators over here. But maybe it's time to actually think about accelerators over here also. So why don't we think of memory as a conventional accelerator and put specialized computation capability that doesn't destroy its cost or other characteristics over here. I think of row clone as a very simple example of that. So we'd like to do more sophisticated things, hopefully, maybe in-memory search. So if you store your database over here, maybe the processor can communicate the queries into that database, and memory can do the search in parallel in its subarrays and provide the results, maybe approximate results that the processor can later focus on and dig into. There are many questions over here which I'm not going to answer. I'll just talk about do you need a flexible and scalable memory interface to do this? And these memory interfaces don't exist today. What is the right partitioning of computation capability? That's an important issue. What is the right low-cost memory substrate? How do you actually do this at very low cost? You can actually do this with 3D stacked memories, and we have papers at ISCA describing how you actually map graph analytics workloads on something like Micron's hybrid memory cube. But how do you do it internally in DRAM is also an interesting question. What memory technologies are the best enablers? I do not believe DRAM is necessarily the best technology for this. There may be other technologies like STT-MRAM, which is also interesting because they more tightly couple logic and memory together. And once you have this, how do you rethink and search algorithms and applications? So one of the difficulties, even with row clone, was finding applications that actually do this copying a lot. Because it turns out, because copies are so expensive, a lot of programmers write software to avoid those copies. But if copies become so cheap, maybe there are different kind of programming models that the programmers can exploit. So this is actually, just to give you that there's more, in addition to row clone, this is a slide that I took from Vivek Seshadri's, my student's presentation, a proposal presentation. These are the parts he's completed as part of his thesis. So he's been looking at in-DRAM gather, scatter, and in-DRAM bitwise operations. I'll talk a little bit about this because I think this is really interesting. We can exploit the chart sharing capabilities of DRAM to actually do and OR in bulk. And take this with a grain of salt for now, but let's assume that we have three rows over here, three transistors that are connected to the same bit line. If you have the ability to concurrently enable three rows at the same time, by chart sharing properties, you actually get a majority circuit. Basically, if you have two capacitors that are charged, then you will actually turn this, this bit line will actually give you a 1. If you have the majority discharged, this bit line will actually give you a 0. So this is essentially what you get. I'm going to skip through the animation. This is the final state. It's really a majority circuit. And you can rewrite this majority circuit as a control row and two other input rows, if you will. And if the C control row is set to 1, what you get is an OR of A and B. If the C is set to 0, what you get is AND of A and B. Basically, you get a bulk AND and bulk OR if you do this. with very little cost. You don't change the DRAM at all, except you need to enable 3 activates at the same time, concurrently. And you need to do a row clone because this is the part you actually destroy all of these with the results once you actually do this computation. So what's the effect of this? Basically, if you are able to do this in DRAM, you can get 20x improvement in AND and OR throughput versus Intel's AVX design, which brings the data all the way into the processor. And Intel's AVX, this is the SIMD vector-wide AND and OR you can do in Intel's AVX. It works really well if you're running the data out of caches. Your throughput is really high with the AVX. But if your data becomes big, and if you're running out of memory, your throughput with SIMD engines that bring the data to the processor actually drops down significantly. Whereas your throughput stays constant if you're always doing things in memory. And this leads to a significant reduction in memory energy as well. So Vivek has actually taken this, actually implemented the fastbit library, which actually does a lot of AND and OR computations. You see a significant performance improvement in range queries. So I think going forward, looking into things that can enable bulk computation in DRAM is really interesting. So if you want to do a Boolean complete logic, we actually want NAND or NOR. So putting not in DRAM is actually pretty interesting going forward.
Taking an extreme, this idea is it starts with a central embedded DRAM that was tried and abandoned. Didn't want from it.
That's been what?
Tried and abandoned. Embedded DRAM. The graphics community,
Yes.
Before the media PhD, when they were awards with the company S3 or something like that, that had this embedded DRAM. The logic process became 30% slower. But then you had an enormous bandwidth and with one chip data movement. What you're talking about is like adding logic inside the memory.
So this one is actually not adding any logic inside memory, right? If you look at this purely analog, you basically activate 3
That's why
rows.
that you're showing, like you're talking about like adding AND and NOR and all the suppositions
Yes.
at the point.
So the hope is that you don't add significant logic. So in this case, you're exploiting the analog computation properties.
We cannot hear. So
Oh, okay.
this is a nice discussion. But
Oh, okay, sorry about that. So the question is, adding logic inside memory actually is costly. How do you actually avoid that cost? So in this case, the cost is really just 3 activates. It's really simple. We're not adding AND or OR in memory. If you add AND and OR, I agree, the cost is actually something that's higher than DRAM manufacturers can tolerate. You can add it at the logic layer, which is still acceptable, assuming you have 3D stacked memory. So I agree with you. But I think the key is finding these techniques that can actually provide you the functionality with what already exists, or almost exists in DRAM. And I believe actually not already exists too, so my students are looking into that right now. Yes?
Here in this case, the original data is lost.
Yes, that's right. That's why you need the row clone also.
Yeah.
So what we're going into is hopefully a bulk computation model in DRAM. Okay. Okay, we can take this to the boat tour perhaps. It's a really exciting topic. Well, let me go into, yes?
a very short one is more on the system level. All these operations to the memory system, but how do you do the synchronization? How do you know that the operation is finished? Or you always assume that it finishes much faster than the follow-up request?
Yeah, you certainly need a programming model that actually enables this.
Oh,
And what's the right programming model is also important. So you need the right interface across the stack. Okay, let me go into one more problem really quickly, which is a combination of refresh and reliable, but I'll motivate it with refresh actually. So refresh is actually one of the fundamental challenges of scaling DRAM. The problem is DRAM capacitor charge leaks over time, and memory controller needs to refresh each row periodically to restore the charge, which means that it needs to activate each row every n milliseconds. And today, typical n is 64 milliseconds, but it's going down. There are many downsides to this. It consumes energy each refresh. It leads to performance degradation. DRAM rank or bank becomes unavailable while it's being refreshed. It leads to some quality of service impact. You can get pause times during refresh. And refresh rate actually limits DRAM capacity scaling. I'll give you some numbers over here. This is from a paper that we published in ISCA 2012. This is device capacity, DRAM device capacity on the x-axis. And this is the percentage of time that the device requires refreshing. Basically, throughput loss of the device for refresh. Today, it's about 8%. And this is something you need to lose. If you keep the same scaling trend, if you do the same calculations that have been going for a long time, basically, if you want to build a 64 gigabit device to increase capacity, we'll be spending 46% of the time of the device just for refresh. And the energy trends are similar, and this, you could argue with these numbers because this actually assumes some utilization values. But regardless, today we're spending maybe 10 to 15% of the energy for refresh. In the future, it's going to be about half of the energy for DRAM for refresh. And regardless of what you assume over here, the trends are really exponential. So how can we actually fix this problem? I think that this is a problem that we need to investigate. I'll give you one potential solution direction, which has been obvious for a while, but we haven't been doing it, because we need to change the interface of DRAM. And that's the retention time profile of DRAM. I alluded to this earlier. If you look at how often a cell actually can retain, how long a cell can retain data, a cell can retain data for much longer than the frequency at which we're refreshing it today, actually for most cells. Most cells in DRAM today can retain data for more than 256 milliseconds. There are very few cells that can not retain data as long. And we're actually designing the refresh mechanism today for that worst case. We're refreshing everything every 64 milliseconds. And we actually characterize this problem significantly. This is true in past DRAM chips and modern DRAM chips too. So how can you take advantage of this? I'll give you one solution direction. And actually this is data from Samsung, from electron device letters in 2009. They've actually seen something similar. In a 32 gigabyte DRAM system, there are about 1,000 cells that cannot retain data for 256 milliseconds. So the key, one idea is we can refresh rows containing weak cells more frequently, other rows less frequently. So to enable this, first of all, you need to figure out the retention time of all rows. Store the retention time in some way in the memory controller into bins. And you can actually do this with Bloom filters efficiently. I'm not going to go into the detail. You can read the paper. The memory controller refreshes rows in different bins at different rates. So if you somehow do this, you get significant reduction in refresh. Even with 2 bins or 3 bins, you can reduce approximately 75% of the refreshes with very little storage cost in hardware. This leads to significant dynamic and idle power reduction in DRAM between 15 to 20%. And this leads to significant performance improvement, about 9 to 10%. And this can actually be higher in some workloads. And the benefits actually increase with DRAM capacity. These are with 8 gigabit DRAM. If you actually have 64 gigabit DRAM, you save energy by 50%. But even the solution is not enough, by the way. If you want to keep energy per access constant, which is what we would like to really do to get good scaling, energy per access is still increasing with this solution. But regardless, I think this is a good solution to explore. And there may be other things. If we can actually figure out this retention time of all rows, which it turns out to be this is the most difficult part of this mechanism. How do you figure out the retention time of all rows reliably? And I talked about this earlier. You can actually do much more things. If you can communicate to the system software or the compiler or the architecture, you can actually do many things. Maybe you can not use some of those pages. If you know the lifetime of data, you can actually map the data with lower lifetimes to those or higher lifetimes to those things that do not require a lot of refresh. Yes?
Is your proposal that you profile it when it's being used or
Yes.
when the thing is...
I'm going to get to that. So the most difficult part is how do you find out these weak memory rows and cells? I'm going to talk about this in a little bit. Basically, we've done a lot of studies. You can take a look at these papers if there is more interest. But how do you actually get those rows? And as I said earlier, it's going to be very difficult for the DRAM manufacturer to actually do this because of this VRT, variable retention time problem. Basically, a cell can switch between multiple states at any time. So you test DRAM. It turns out the retention time of a cell is 100 seconds, and you test it for days and days, it's 100 seconds. But 4 days later, it drops down to 64 milliseconds, or 32 milliseconds. How do you figure out these cells? This problem is going to be increasingly difficult. And our solution is looking into online profiling of DRAM in the field. So maybe the manufacturer manufactures DRAM without testing it fully, but put some ECC, maybe virtualized ECC, like Motan is doing at UT. So we can initially protect DRAM with ECC, and the manufacturers are in the right mindset for this. They're putting ECC into DRAM. And the system periodically tests parts of DRAM, maybe the parts that are going to be used. And over time, it adjusts refresh rates and ECC accordingly to give the illusion of a reliable DRAM, if you will, or make it reliable in the field. And that's the goal that we're looking forward to. Basically, we can optimize DRAM in many different ways and mitigate errors online, hopefully without disturbing the system and the applications. I don't have a solution, I don't have a full solution over here, but this is the goal. Yes?
How do you see things like MC log and this sort of thing working with this idea?
Say it again?
there are some daemons like MC log with almost machine check exemptions, where they log things that have been corrected in the DRAM. How do you see this sort of daemons or logs or whatever fitting into this idea?
So I think that's a current implementation thing, but I think that could actually be used to make it work, right? Because if you figure out the errors, you can actually, if you have a mechanism to allocate ECC to different rows, then you can actually allocate more ECC to those parts of DRAM that happen to be causing a lot of these MC log errors, right?
Just another question. You mentioned the refresh problem before, but aren't you trading the refresh problem to the ECC problem? Because what you're saying here in bullet number 2 is that you periodically have to test the cells because of the VRP. Now, we don't have such a high amount of refresh anymore, but now we're periodically testing the ECC.
That's right.
So,
but you want a system, so that's a really good question actually. I see two ways. You always refresh DRAM at a very high rate versus you only have ECC and never refresh DRAM. So we're trying to get to a solution that's somewhere in between without the downsides of both ends.
But you do expose yourself to some problems then, right?
Absolutely, absolutely. I mean, this is not done yet. I mean, certainly you need to ensure that the system still operates correctly. That's why you need to have the right amount of ECC to begin with.
If you reduce the ECC and at some point the DRAM cell goes to the 64 refresh requirement, then in that time, before you test it, you expose yourself to...
That's right, as long, if you have a good model of DRAM. I'd recommend looking at our DSN paper this year. It's called Avatar. It has a good model of DRAM that takes into account all of that. And we can talk about it later. Okay, so let me jump into one more thing, and then we'll finish the DRAM part. Any questions, or am I going too fast now? I'm fine? Okay. I'm afraid you will tell me that I should slow down by 10x. Okay, let's talk about latency.
It wouldn't make any difference.
All right. So latency, I want to talk about latency because this is an ignored part of DRAM for a long time. Well, I believe it's really important. So if you look at the DRAM latency capacity curve, it looks like this. Basically, the capacity has increased exponentially over the years, whereas latency reduced very little, 20%. This is the row cycling latency. But latency continues to be important, and it's a critical bottleneck or response time sensitive workloads, especially if you have a single thread where you need to access DRAM, and it's really important, you get bound by that latency. So what causes this long latency? I'll talk about two things. One cause is microarchitectural, the way we design DRAM chips, and I'll talk about its solution very briefly. And the second cause is the waste. Let's talk about the first cause. If you look at a DRAM chip, it consists of a cell array, this is a bank, and the bank input and output. This consists of subarrays. There's some latency in the subarray access, and there's some latency in the I/O circuitry over here to drive the data out. I'll say that the subarray latency is dominant because you can actually create a lot of tricks over here to hide that I/O latency, like prefetching. DRAM manufacturers do that a lot actually. So let's take a look at the subarray latency. So why is this subarray so slow today? This is the DRAM cell. You need to sense the data in the capacitor through this bit line, and you need a sense amplifier to do that. It turns out to do the sensing reliably, the sense amplifier needs to be huge. In modern DRAM chips, the size of this is about 100 times the size of a cell. So because of this, what DRAM manufacturers do is they take a sense amplifier and string together many cells on the bit line such that they can amortize the cost of the sense amplifier. So you get a long bit line with 512 or 1024 cells. This is good because you get small area now. The downside is you get large capacitance on this long bit line, so you get high latency and power whenever you want to access a single cell over here. So there's a clear trade-off between area and latency in DRAM. You get long bit line, you can make it faster by chopping it up and adding more sense amplifiers. But if you want to be smaller, you got to go here. So let's take a look at this trade-off. This latency on the x-axis, normalized DRAM area on the y-axis. If you want to be cheaper and faster, you want to be here, ideally. But today's DRAM actually makes, commodity DRAM makes the trade-off over here. Now, if you actually want to be fast, you can pay an arm and a leg for some fancy DRAM, reduced latency DRAM, or fast cycling DRAM, where you get the short bit lines. Your latency is lower, but you really pay the arm and a leg for it. So it's used in very specialized routers, for example. So our goal is to achieve this. So how do we achieve that? If I told you with DRAM technology, I'll give you this, and I already have a solution, I think you should kick me out of here. But, because I think it's very fundamental, we're not going to be able to get DRAM over here. But we can approximate the best of both worlds by using heterogeneity. So long bit line has some reds and some greens. Short bit line has some reds and some greens. So we're going to try to get to the greens as much as possible. We'll start with the long bit line architecture, which provides us a small area. And we'll create a low latency portion in it, which is the short bit line over here. Basically, we'll kind of have part of it that looks like this, such that we can access it fast. And you can do it by segmenting the bit lines and adding isolation transistors in the middle. So this is called the tiered latency DRAM, this Please work. Basically, you get small area using a long bit line, but when you isolate, when you turn off these transistors over here, you get an area that has low latency because you have very low capacitance over here. And if you do the data allocation nicely, hopefully you access this area mostly. So what's the characteristics of this? This near segment, if you have 32 rows in it, and if you have 480 rows in the far segment, you can reduce the near segment latency by 56%. Whereas far segment latency unfortunately increases because of the resistance on the bit line. And this is the power characteristic. So if you're running out of this near segment, most of the time you're power efficient and you're fast. And this comes at a DRAM area overhead of 3%, mainly due to these isolation transistors. So this is actually, basically, near segment breaks the trade-off. Unfortunately, far segment takes us over here. Now we have heterogeneous memory within a chip, heterogeneous latency within a chip. So we need to really manage it to get good performance out of it. This is really a substrate that can be managed by the hardware or the software. And we looked at many potential uses. I'll give you one really simple use. You can use the near segment as inclusive cache to the far segment, hardware managed. And I'll give you results with an LRU cache. Or you can have an exclusive cache if you don't want to lose capacity. You can do profile-based page mapping by the system software or the application. One thing that doesn't work is simply replacing DRAM with TLDRAM and adjusting the latencies of the controller, because your frequently used data doesn't magically get mapped to that portion of DRAM. You need to be a little bit more intelligent about it. So what if you do the dumbest thing? Basically, whenever you access a row, you clone it to this near segment and cache it in the near segment. The next time you access it, hopefully the access is faster. It's an LRU cache, basically. If you do that on a large number of applications, you get significant performance benefits. I believe this can be increased by doing more intelligent techniques. And your DRAM energy actually reduces significantly also. So this kind of techniques that change the microarchitecture of DRAM with little area cost. And I believe little is, in this case, 3%. Like if you talk to DRAM manufacturer, they will actually tell you to go away if you tell them you have 3% additional area cost. I think we need some other techniques to actually reduce that area cost, but still get good performance benefits with some latency. And maybe some of you will design that. Let me talk about one more thing that points out to some of the waste in which we design the DRAM today. And that's really the conservative timing margins. If you look at DRAM today, the latency is really determined to cover the worst case. Worst case temperatures, basically the latency is set to cover operation of DRAM at 85 degrees. But in common case, you don't operate your DRAM at 85 degrees. And worst case devices, the latency is set to cover the worst case DRAM cell with smallest charge across any acceptable device. And this leads to large timing margins for the common case. So the idea, our idea was to have adaptive latency DRAM. Again, this is Lee's work, optimizing DRAM timing for the common case. So what is the common case? It's the current temperature you're operating at, and the current DRAM module. And you can actually do the mechanism that I will describe today in real systems. I'll give you some real system results. So why would this reduce latency, first of all? If you look at the common case, a DRAM cell can actually store much more charge in the common case. If you look at DRAM, most cells are really strong. They're big, they're large, so they have a lot of charge storage, and their resistance is low. And also, at low temperatures, there's a lot of charge. The charge doesn't leak as fast. So having more charge in the DRAM cell leads to faster sensing, faster charge restoration, and faster pre-charging as well. Basically faster access. So why don't we optimize DRAM timing parameters online? To be able to do this, you need two components. And I think this is a thing that can be done reasonably easily today. DRAM manufacturer can provide multiple sets of reliable timing parameters at different temperatures for each DIMM. And the system can monitor the DRAM temperature and uses the appropriate DRAM timing parameters. So the key is over here, monitoring the temperature, which is done today. But how do you figure out the reliable DRAM timing parameters? This is actually another optimization that can be done online if you have that online profiling system that I discussed earlier. But we've actually done it with an offline study. Donkyo characterized 115 DIMMs, approximately 1,000 chips. And at 55 degrees, you can reduce DRAM latency read latency by about 30% and write latency by about 55%. And you can read the paper for detailed study of different DIMMs and different parameters. And you can actually, by figuring out what's reliable timing parameters, you can actually, on a real system, like this AMD system, you can change the DRAM timing parameters and figure out the effect on the application. I'll give you very quickly, on this system, Donkyo ran a bunch of applications and figured out that you can improve performance significantly for a single core, single application, if it's memory intensive. By using these reliable reduced latency parameters at 55 degrees, you can improve performance by about 6%. And if you're actually running multi-core applications, because memory latency becomes a bigger bottleneck over there, you can improve performance by more than 10%, about 14% on this real AMD system, if you can figure out these reliable timing parameters. So I think this points out some of the wastes with which we're really setting the parameters in the memory system today. Refresh is one example, latency is another example, bandwidth is another example actually, which other people are also working on. So these are things that I will not talk about, but maybe we can reserve them for later. Let me switch to the next direction, unless there's a really quick question right now. Okay, let me switch to the next direction, enabling emerging technologies. I'll talk a little bit about that. There are some emerging technologies that are resistive, that seem more scalable than DRAM because they're resistive. One example is phase change memory. This is actually really old technology. It's used in rewritable CD-ROMs. Basically, you can store data by changing the phase of a material, chalcogenide glass, and you can read data by detecting the material's resistance. And the material exists in two states, amorphous or crystalline. And the way rewritable CD-ROMs operate, they basically shine light on it, and based on the optical reflexivity of the different two states, you can determine whether a 0 or 1 is stored in it. But people have developed read devices at the lower level today that can be operated reliably and quickly, that can sense the resistance of the two different states. That's why this has become really interesting recently. I'm not sure if it's really interesting going forward, but I think it's an example of a technology that's more scalable than DRAM, and if it's enabled properly, that can change how we can design memories going into the future. I already told that ITRS projects that this is actually more scalable, and it was prototyped by IBM at 20 nanometers. And you can actually chop up the resistance range such that you can store multiple bits per cell, because the resistance range is large between the two different states. The problem is these emerging technologies, like phase change memory, have many shortcomings. The key question that I will briefly discuss, hopefully, is can we somehow enable them to replace, augment, or surpass DRAM? So why are these different? Very quickly, when you have charge-based memory, as the charge storage unit reduces, the capacitor or the floating gate in flash, it becomes difficult to place and control charge. And reliable sensing becomes difficult also. That's why we're having problems with DRAM as well as flash. So some of these technologies that seem promising, they're all resistant. Phase change memory, you inject current to change the phase of the material, and the resistance of the material is determined by that phase. In STT-MRAM, spin transfer torque magnetic memory, you inject current to change the polarity of a magnet, and the resistance is determined by that polarity with respect to a reference layer. In memristors, RRAM or ReRAM, you inject current to change the atomic structure, and resistance is determined by the distance of the atoms. And you can have read devices that can read these and distinguish between these different resistances. I'll talk very briefly about PCM. Basically, it has some pros over DRAM. It scales better, it's non-volatile, and it has low idle power. So hopefully the refresh problem goes away. The downside is it has higher latency, especially write latencies are significantly higher. It has higher active energy, especially write energy is significantly higher, because you actually need to melt the material. It has low endurance. A cell dies after 10 to the 8 or so writes, because you actually, to melt the material, you expose it to very high temperatures, and the contacts degrade. As a result, at some point, you're not able to read or write to the cell. And there are some other reliability issues. So resistance drifts, for example. So that you may need to actually do a refresh of the cell as well. So basically, we have a memory that has greens and reds. So how do we actually use it as part of the memory system? We need to somehow mitigate the shortcomings it has and find the right way to place this memory in the system. And even though I'm going to talk about PCM, take this with a grain of salt, think about this as some emerging memory technology. I think what we're going to talk about is going to be fundamental to any emerging memory technology. So when we first started looking at this is a cartoon from 2008 or so actually. This was the current state of the art in memory. Basically, we thought initially some of the DRAM will be replaced by PCM, and eventually some scalable technology will replace DRAM. So this is hybrid phase change memory in DRAM. Moinder Qureshi was also looking at it at that time. But we thought this was the more aggressive solution, if you will. So we validated that. I'll give you some results with this, and then we'll turn back to this one over here. So we did this study where you take a DRAM-based system and replace every single DRAM cell with a phase change memory cell. Change nothing else in the system. And we surveyed prototypes of phase change memory that were published in device and circuits conferences. And we wanted to derive parameters for phase change memory for a feature size of 90 nanometers. This is a very difficult task actually. You go through all of these papers and they all say a different thing. But eventually we settled on some latency values. I'm going to show you results of what you would get with a memory that has 4 times the latency of DRAM for reads, 12 times the latency of DRAM for writes, an endurance of a cell dying after 10 to the 8 writes, and when you access a cell, when you read a cell, you get twice the energy of DRAM, and when you write to a cell, you get 43 times the energy of DRAM. Now if you take a memory like this, replace DRAM with this kind of memory, the result is pretty bad actually. Basically, you get 60% performance degradation on these scientific applications, some of which are memory intensive, some of which are not. You get 120% energy increase, and your memory dies after $500. That sounds like a bad idea, right? And it's a bad idea, I think. So how do you actually fix this problem? What we did in this paper was actually to organize the row buffers in phase change memory such that you can do better caching, such that you don't... So if you have a memory technology like this, ideally, you don't want to write to it, and you don't want to access it. So it's good for cold storage in a sense, if you want to replace DRAM with it. So you want to do really good caching around it. So that's what we did actually. And if you do that, for these workloads, your performance degradation goes down to 20%. Your energy becomes on par, but take this with a grain of salt. This very much depends on the energy models you have. If refresh is not a big component, this will increase. And the average lifetime becomes 5.6 years. So it sounds better, but it's not that good because your worst case lifetime is much shorter actually. There are some applications, there are no guarantees you get. You can actually write an attack program that destroys your memory relatively quickly. Intensive applications see large performance and energy hits, unfortunately, so even though this 20% is average, maybe there are some applications over here that lose 100% performance. And perhaps we used optimistic parameters for a technology like this. And this is still not clear to me because we don't have this technology out there. I think it's really important in this research, but it's not clear if we have used the right parameters for this kind of technology. So I think a more viable solution, given the downsides of technologies like this, is to design hybrid memory systems, where you have technologies like DRAM that are fast and durable, but they need to be small because they're leaky, and they're high cost, and they're high power. And technologies like phase change memory, or maybe some other type of DRAM that is large, non-volatile, and low cost, but slow. It may wear out, it may have higher active range, and different technologies may have different reds and greens over here. But if we can design the hardware and software to manage data allocation and movement, perhaps we can achieve the best of both worlds, or multiple worlds, and expose the greens as much as possible. And this is already happening, I think. We're already getting 3D stacked DRAM that's high bandwidth, low latency, high energy, expensive, that's why it's small. And maybe commodity DRAM that's similar to the DRAM that we have. Slow, low bandwidth, lower energy reasonably, but high capacity. And I think this is going to happen more and more into the future. Of course, this comes at a cost, the complexity. So even with technologies like this, I'll give you one example of where we are in this hybrid memory system. But if you have a technology like this, you can still use it for a good purpose. So if you're streaming through memory, so if you can somehow figure out which accesses are good here versus good there, you can partition your data out. And I think we need to find the primitives to actually communicate down to the layers. And what are those primitives is really an interesting question. One primitive, I think, is random access versus streaming, for example. If you can somehow figure out which data you're streaming through and you can communicate across the layers, maybe it makes more sense to not waste valuable memory like DRAM for streaming accesses. Because you can really design your other memories over here and the memory hierarchy for good streaming performance. Because you can have row buffers where you can stream your data through. As a result, you don't waste the memory that has very good random access performance for streaming accesses. Today we're isolating DRAM for that purpose, I think. In fact, if you're streaming through data, maybe you can design systems that are based on tape, and you can do a lot of buffering in the system, such that you eliminate all of those expensive memories in between. Anyway, basically, where are we today? This is data from this paper. People have improved this over time, but I'll give you this result. This is performance comparison of 16 gigabyte phase change memory to 16 gigabyte DRAM. There's a huge performance gap over here across about 100 applications. If you use a hybrid memory system where the memory controller figures out what is streaming and what is random access with good locality and partitions data between DRAM and phase change memory, this is where you get. Basically, we're still not there. Even with a hybrid memory system, we're still far off from the performance of DRAM if you have a memory technology that looks like PCM. But I think there's hope. There are some other technologies, I think this maybe partially answers Trevor's questions over there. There are some other technologies that may seem more interesting. I'm not going to go into this in detail, but STT-MRAM, as I said earlier, you store data in terms of the polarity of a magnet. You have a reference layer and you have a free layer, and you can change the polarity of the free layer if it's parallel versus anti-parallel, that encodes a 1 or 0. And if you actually take this as main memory, it has characteristics that are better than phase change memory. You get higher write latencies.
Power.
Oh, okay.
It's not you.
Oh, it's not mine. Okay.
We blew this out.
Well, I can go on.
Let me ask you a question.
Sure.
And a former Yale boy. So it appears that all their proposals require software support. So how am I as a DRAM manufacturer going to rely on my product on somebody else? Number one. Number two, in a data center, you cannot permit heterogeneity, different types of DRAMs in the data center, or everybody must have the same DRAM for your software to run?
So let me take the first one. First of all, not all of the solutions that I've described require software support. The adaptive latency DRAM, I think you can perhaps do it today if you're intelligent about your DRAM. But most of them, yeah, what I'm advocating requires software support, I agree. And I think the space is changing. I think people need to... we have memories that are bifurcating today, so if you look at...
It's orbiting much more than anything else, so...
That's right, software is definitely a problem, but we need some support from the system. It could be the software, it could be the memory controller. But there are people who are willing to actually change their software, this is one example of it, to actually get the performance and energy to lower levels. So maybe some parts of the space will be less willing to move to that kind of model. But I think once they feel the energy and performance issues, they're feeling it over here, they will be able to move some of their software at least. I think it's going to be gradual. I'm not suggesting that everything will change.
For 40 years. And we keep on. All right.
I agree with you. Things will not change overnight, Guri. But I think there's hope that things will change because people are already doing it for other reasons over here.
There always is hope.
Yes.
So I guess we've got some time. I'll go back to you talked earlier about the in-memory processing type stuff, and one of your examples was a search. You could send something off and it would search through the memory to find something. How do you do that without access to TLBs to know that you're not finding data that belongs to somebody else that you shouldn't be looking at?
Sure.
How do you provide security if you don't have TLB access?
So that's a great question, and actually I didn't go over it in detail, but that's something that also, if you want to do that kind of thing, you need to look at what is the memory model that you provide. And one potential thing is to extend the virtual memory model such that you can do ability to do translation on that other side, if you will. And we're actually looking at that. That was actually on Vivek's proposal slide, virtual memory support. But there are other models potentially also. Maybe you have segmented access models. I think that's something that people need to investigate. And that's a critical component.
Are you through with your slides?
No, I'm not through, but I can go on.
So do you want to finish this up or? Not.
I can finish it up, I guess.
No, so you have slides, the power went out. Is the power now back on that you can finish the slides, or?
I don't think power is back
The
on.
whole island is without power.
Yeah.
So,
I can summarize and finish right now, such that.
so I don't know. First of all, I absolutely want to congratulate everybody for enduring this. I should say not this presentation, but these presentations. There's some hands up. There are questions. Trevor, you had a question?
Yeah. So, these new memory technologies are interesting.
Can't hear you.
Louder.
Speak up.
These new memory technologies are interesting. It seems though that things like DRAM and flash continue to live way beyond expectations. If you look at the old ITRS model, they should have fallen over at 20 nanometers, but they're going strong. Is there ever going to be a day when we're actually going to use PCM? I mean, when you wrote that paper with Doug Berger's company when you were at Microsoft, it looked promising in those days. But it's sort of, I've not seen one. If you look, future maps of DRAM manufacturers like Samsung and so on, they've got DRAM going all the way down to 10 nanometers, but they don't, PC RAM's like not on the slide anymore.
So I think that's true with any new technology, in my opinion. And there are good reasons to keep the current technology, right? DRAM and flash, as long as you come down, it's a good idea to keep scaling them down. But there are clearly difficulties in doing so. The cost is increasing, certainly, and there are reliability issues. So I don't have a good answer for you. I think maybe PCM will come and go, and maybe it'll come again, depending on what the manufacturer will find out.
I remember the HP said they were going to be in volume production in 2013. I think it's 2015 now, right?
That's right, yes, that's right. So maybe it's always out 5 years, but there may be at some point. I think it's important to do the system level research to potentially enable technologies like this. Whether they will ever appear or whether they will appear 5 years from now, I don't know. I don't know the answer to that. But I think I'll give you one example of a successful technology. Flash was in that position for a long time, right?
Yeah, but Flash had a niche application, which was MP3 players.
That's true.
That got volume, and now it's the most common storage.
That's true. Maybe these technologies need their niche applications also, and I don't have that question for that because I'm not designing applications. But I think that it's important to do the research to figure out what should be that application also. And if I knew the exact answer to your question, I probably would be starting a company.
The DRAMs are going to go monolithic 3D like Flash has to give them another way, so they don't have to shrink the memory stuff.
For DRAM?
Yeah.
Yeah, I think.
I'm not talking about die stacking. I'm talking about
really 3D.
Yeah. Like they do in Flash in monolithic.
And I believe manufacturers are looking into those solutions. I think if they find a good way, I think they'll do it. I agree that that's a good direction to explore.
So I think Gauri's point was well taken, that 40 years from now, we may still be where we are. But if nobody does these things that Onur is doing, then we're guaranteed that 40 years from now we'll be where we are. And so it's important to have people like Onur that are exploring all these cockamamie schemes to figure out, to fit, so as to enable some of these things to happen.
Well, it's not only me, it's also Trevor. we're in this together. And others.
Gauri's just an old geezer.
I'm sorry? Are there any other questions? Go
I
ahead.
have one. I mean, these ideas of processing in memory have been around for a while. I mean, there was like Berkeley IRAM and all kinds of things. So what's different and new now? They didn't succeed back then, right?
So, yeah, I agree with you. Let me take that. By the way, it's much older than IRAM. It's 1970.
Sure.
Harold Stone. Harold Stone has a really nice paper, Logic in Memory.
In fact, after Harold Stone, there was Peter Kogi, and after Peter Kogi, there was Tom Sterling, and after Tom Sterling, there was IRAM.
You're just reinforcing my point.
So what's different today? I think when people have looked at that point in time, they were idealistic. And that was good. I'm not saying this as a negative thing at all. But they wanted to do, a lot of those papers, if you look at them, they really want to put a processor on the DRAM. I think it's going to be very, very difficult. With die stack technologies, you get close. You get with a controller and DRAM, and that's happening already. That's one of the reasons why this is really interesting, because you have the die stack HBM, HMC technologies that you already have. That's why I think you can do something on over there. But the other approach that I believe no one has examined is this bulk computation in DRAM. What can you do? Very little. Not put a huge processor over there, but what is the minimum that you can do over there and get the biggest bang of the buck, bang from your buck? I don't think anyone has examined that at that point, because everyone was looking at it from an idealistic view rather than a cost-sensitive view. And this is not to suggest that the research was bad. I think it's really important, actually, that was leading the field at that point in time. But maybe it's an idea, its time has come, because we have these technologies that are potentially enabling it, 3D stacking, and we can look at things from a more cost-sensitive view, and we have all these scaling issues anyway. And maybe DRAM manufacturers will be more willing to put things inside there because they're running into these scaling issues. And they actually are. They're interested in finding out how can they enable a different markets with potentially specialized DRAMs.
Yeah, I mean, the stacking to me is a bit conceptually different, right, than putting the logic right there into the next to the memory cell in the same die, right?
So it's conceptually different, but it enables the benefits that you would get.
Sure,
it basically puts you away from that memory bus. Basically,
Sure.
you get high bandwidth, low latency, and you don't need to go over the interconnect that goes to the processor.
Sure, but that's not what you're trying to do, right? You're trying to use the existing memory cells and the logic that's in the same die, right, to do more, right?
So that's one direction. I talk about that direction, but we have another direction which I really didn't talk about,
Yeah.
where you actually, what can you do in that logic layer? And we have actually 3 ISCA papers. For example, in one, we map a graph analytics application into an interconnected hybrid memory cube devices where you have controllers and DRAM die stack. And you have a kind of a specialized single processor inside there.
So why isn't that the right answer? Let's assume the DRAM manufacturer is not willing to do much, which I think is a fair assumption. And the programmer is clueless, which is another fair assumption. So what we do is we take the DRAM given to us by the DRAM manufacturer and augment it with doing some stuff on the chip, next to the chip, provided by the, I don't know, the integrator, the microarchitect, if you will, to do in hardware this monitoring to determine refresh cycles, for example, to determine when something needs to happen, for example.
Yeah.
And not think in terms of, I think Gauri's right about the programmer. You know? Not think that the programmer is going to change his programming model. You know, how many programmers understand what an unaligned access is to memory, for example? You know, which is hardware baby food. And do that augmentation on the chip, not by the DRAM manufacturer, but by the microarchitect putting it together into a system. Other questions? Go ahead.
The in-memory computation, they are fascinating, but doesn't it shift the problem a little bit to the analog processing inside the sense amplifier? Because I can imagine that designing the sense amplifier, which itself is still a critical component, becomes even more critical because now noise margin problems and things like that should be worse.
So I agree with you. I think there needs to be more thought into that analog processing that happens in DRAM if you want to enable in-memory processing the way I described it. And those are the things that I really cannot do research on. That's not my expertise, but I believe those are some solutions that no one has explored so far. People have explored designing sense amplifiers just for capacity, but not to do this kind of analog computation in DRAM.
And I would say something like that is probably the DRAM manufacturer should step up. I've been given the signal that this thing is way over time. Did you videotape it, by the way? Or not? Did you videotape it? Yeah. Good, so then people can take it and play it at 1/10 the speed. and that's good. I did have a question earlier, but I'm going to not deal with it. No, I'm not going to deal with it, but something that scares the shit out of me is this hammering thing that he talked about earlier. and something I'd like to get into, but we just don't have time. We're over.
Well,
We're over. Let's thank Professor Mutlu for his.